This is Unit 2 for the Advanced Functions course, the first lesson on polynomials. The overall unit is talking about polynomial functions. Today's lesson is just about sort of what is a polynomial. Let's get a definition, learn some of its basic properties before we move on to later in the unit as we seek to expand on our knowledge from grade 11. A polynomial is a very general thing. It's a very broad category, but there are some specific rules that it has to follow in order to be considered a polynomial. And you can see, like, our first exercise here is just asking, which one of these different expressions would represent a polynomial. Now, an expression, just so we know, an expression is something that is not equal to anything. So suppose you had, for example, let's just write it out like this and sort of make this clearer. So a polynomial expression might be something like 3x squared plus 2x plus 1. A polynomial function might be f of x equals 3x squared plus 2x plus 1, and a polynomial equation might be 3x squared plus 2x plus 1 equals 6, right? Where all of these things are, of course, very similar. We just want to be precise about which word we use when we are talking about a function versus an equation versus an expression. None of them are, it doesn't make them different in the sense that one is a polynomial and one's not. It's just rather to make the difference between when you see those three words, what does it actually mean? So a polynomial expression is something that's not equal to anything. It's just by itself. A function, remember, is a set of instructions with an input, and then the instructions are over here and it would produce an output. And then an equation is more like, what would be the value of x that would make this situation here actually work. So in order for something to be a polynomial, you can see what it has to look like right here. It is a series of terms that are either added or subtracted together, and each of the terms contains a coefficient. Okay, that would simply be the number in front of the variable, and then a variable to a whole number. Whole number. I should say natural number, because it's only positives. So let's say natural number exponent. What do I mean by that? I mean the exponent has to be a whole number, i.e. 1, 2, 3, 4, 5, 6, 7. And it can't be a decimal, and it can't be negative. Okay, so it can't be a fraction, can't be a decimal, can't be negative. Okay. Okay, so it has to have addition, it has to have coefficients. Now the coefficients can be fractions, that's fine. The exponents on the variable must be whole numbers. Okay, and again, I said natural numbers because that starts at 1. Whole numbers starts at 0. I mean, I guess technically it could be 0, but of course we don't normally write x to the 0 because we know that x to the 0 is just equal to 1, right? So we don't bother really writing it down. X is the only variable in the polynomial. A polynomial expression has only one variable. Okay, the AO is the term without a variable. That would be a constant. AN, which is the term at the very front, typically, of the polynomial, it's the one that's attached to the largest power of x. We call that the leading coefficient. For example, 6x to the 5 minus 2x to the 4 plus x. We would say 6 is the leading coefficient because it is the number that is attached to the highest power of x. Normally, it's only one variable, and the powers are in descending order, which is to say we don't normally write this like this, even though they are the same. we usually write them in the lower one as opposed to the upper one, because you know, it just makes it easier to read it, you know, if we all follow the same pattern. So let's go and do a quick exercise here where we're just looking at what makes a polynomial expression and how do we know. So let me say this one is a polynomial, and in terms of y, it is the sum of two terms with whole number exponents on x. Okay, that's a polynomial. This is a polynomial, right? And again, it would be for the same reason. X to the 5 is okay. This is a fraction, but that doesn't matter. I mean, it can have fractions as its coefficient. It just can't have fractions in its exponent. So that's fine, that's fine, that's fine. There's nothing there that contradicts any of the rules in terms of what is a polynomial. And again, the reason would simply be the same as above, except it's 4 terms. But other than that, it's the same as above. So let's write 4 terms, same as above. Okay, now the other ones are all not polynomials. So no, no, and no. These are different kinds of functions, different kinds of expressions. They do mean something, they just aren't polynomials. Let's look at why not. In the first one, here you have 2 terms divided by 2 terms. That's no good to us because the only way for something to be a polynomial is if all the terms are added or subtracted. You can't have something being divided like this on the bottom, at least not something with a variable. So maybe a better way of saying what I said up here would be there is an x in the denominator. And if there's an x in the denominator, you don't really have a polynomial. Okay, you have something else. This would fail for the same reason, right? We would just write x in denominator. And as soon as you see that, you know that what you have is not a polynomial. This one fails for a couple of reasons. Number one, recall that a negative exponent is the same as a positive exponent flipped over the division line. So remember, if we were to say something like 4 over x to the negative 5, you could bring that x to the 5 up to the top and then change the exponent from negative to positive. Similarly, if we have 2x to the negative 3, we can send that x underneath the division line and then make the exponent a positive. But you'll notice as soon as we do that, of course, x is in the denominator, so you can't have x in the denominator in a polynomial. Another way of looking at this one is you could just say the exponent on x is negative. As soon as you see that, it's not a polynomial. It's immediately not a polynomial. The second reason this fails is because root x, remember, root x is equal to x to the power of 1/2. That was the relationship between square roots and exponents. And obviously, x to the 1/2 also fails to be a polynomial since it is not a full number, a whole number. It is a fraction, right? It's a decimal. So there's lots of reasons why this middle one fails. I mean, you pick any of them. You could say x to the negative 3 is not allowed. You could say root x equals x to the 1/2, and neither of those are allowed. That is not allowed, and that is not allowed, right? So either one of those reasons would be good ones to reject that one. So again, there's nothing really special to this. It's just recognizing different types of functions. What does a polynomial actually look like? To be a polynomial, you can add or subtract terms. You can only have terms that contain x to the power of a whole number. So 0, 1, 2, 3, 4, 5, 6, 7, etc., etc. Cannot have a negative. You cannot have a fraction. Now, the important things about polynomials. The first thing we're going to say is that the domain of every polynomial function, no matter what, is all real numbers. There is never a restriction on any polynomial function. Okay, the domain is always x belongs to real numbers. Now, the only situation you could be in where a polynomial has a restriction is if it had a context. So, for example, if you imagine a common polynomial like this one, where we might launch a rocket with a speed of 50 meters per second from a height 1 meter off the ground, that polynomial will have a restriction on it simply because of when, let's say it hits the ground, it would hit the ground about 5 seconds, 10 seconds later, give or take. And this this parabola, it doesn't have a restriction mathematically, right? Like mathematically, this thing could just keep going there and keep going there. But in terms of the model, it only actually tracks the rocket's height in between, let's say, approximately 0 less than equal to t less than equal to 10. Again, it's not going to be 10 perfectly, but just bear with me for this. I don't want to bother calculating it. So you might have a restriction in a polynomial, but if you do, it only comes from, let's just write over here, the exception would be from a context. So if your function represents a situation, then sure, it could have restrictions on it. But those restrictions would correspond with the physical situation that the function was connected to. It would not correspond to the math itself. There's no reason, for example, you couldn't plug in t equals 12 into this equation. It's just if you did, you would get a negative height, and probably that's not where the rocket is at that time, right? Probably the rocket hit the ground, bounced off of it a little, and then landed over here or something like that, whatever. So the model really doesn't include that section or that section. And you might restrict the domain for that reason, but you never restrict the domain for any mathematical reason. The other thing to know about a polynomial is the term its degree. Its degree is the highest exponent in the expression, and let's just clarify that. The highest exponent of x, right? So for example, if you had one that was like 10 to the 6 x squared plus 3x, the degree of this is degree would be 2. Not 6. So I just don't want you to get the wrong idea there. It says the highest exponent, but when they mean the highest exponent of x, right? Whatever the highest exponent on x is, which is the 2. You can have a regular number to whatever exponent you want, and that doesn't affect the domain. So in this example right here, the degree of this function, the degree would be 3, and that's a really important thing to understand about polynomials. Most of the time, we write polynomials in descending order. So normally, you will see the degree on the very first term, because usually it's written in descending order. You start at the highest and work your way down. We do that to be convenient, right? Because the degree is really important, and we want to know it right away. Now, these things have names up to quartics and quintics. We don't really go beyond quartics, really, for our purposes, but we could. I mean, once you see how it works at 3 and 4, you can extrapolate how it will work for 5, 6, 7, 8, 9, 10, etc., etc. So, a polynomial, it is possible that a polynomial function has no x in it at all. For example, f of x equals 4. That is a polynomial, okay? Because remember, it does have an x in it. It's just that x is to the power of 0. And it's okay if something's to the power of 0. It's not okay if it's to the power of -1. X to the power of 0, remember, is just equal to the number 1, so you normally don't bother writing it down. This is a polynomial, and we would call it a constant. A linear function might be something like f of x equals 1/2 x minus 1. That would be a linear function. You can see that its degree is 1, because the highest exponent of x is a 1. So that's what they're saying here with degree is 1. And that we know creates a straight line. A quadratic is degree 2, because a quadratic might be something like, 6x squared take away 10x plus 1, something like that. And the highest exponent of x is a 2. A cubic has a highest exponent of 3, a quartic has a highest exponent of 4, a quintic has a highest exponent of 5, etc., etc. Once you get beyond 5, really you don't need to know the name anymore. You can just say it's a degree 8 function or a degree 6 function or whatever if you need to name it. Notice that in all of these situations they have a restriction. It's not a domain restriction, because remember we already said none of these ever have a domain restriction. It is a parameter restriction. In other words, your linear function cannot start with 0x plus b, which should make sense to you, because if you have 0x, this is actually equal to 0, and now you actually just have a constant. You don't have a linear. Again, we could do the same analogy. We could look at the second one and go, well, if a is 0, then I have 0x squared plus bx plus c, but 0x squared is really nothing, so really all I have is bx plus c, which is a linear, not a quadratic. So that's why they're writing that little restriction there. Of course, if the leading coefficient is a 0, you don't really have that type of polynomial. It says there are at most n plus 1 terms of a polynomial function of degree n. That should make sense to us, because if there, for example, if n equals 3, then there could be 4 terms maximum. There would be a cubic term, or let's do it the way they did it, sorry. So there'd be a cubic term, a quadratic term, a linear term, and a constant term. And there could never be more than 4, because what would the other term be? Either it would be something that doesn't fit one of those, in which case it's not a polynomial anymore, or it would be something higher than degree 3, which would mean it's not a cubic anymore. So this is what they mean here, where there's n plus 1 terms maximum. So let's go through just again sort of getting the hang of this. How do you do these, like recognize these things? So again, if they're not in order, remember you want to put them in order. So what type is this? This is a linear. It is degree 1. Its leading coefficient is a 7. Recall, leading coefficient is the number attached to the x with the highest power. This one, the type would be a quartic. Sorry, doesn't look very good. Try that again. A quartic is degree 4. Its leading coefficient is 3.7. Again, degree 4. Leading coefficient of 3.7, and I just looked at my little table above for what it's named. This one would be a quadratic. It's degree 2. Its leading coefficient is a -3, right? This value here beside the t squared. Now this one is, you might look at this and think, is this even a polynomial, right? Because it has multiplication of terms. Multiplication of terms is okay, remember, because it's just a, if you imagine like expanding them, you could see how this would turn into something that looks more like a polynomial. For example, if I type this one out, x minus 2, right? So that's the function that they gave me there, right? F of x is x times x plus 1 times x minus 2. If I expand that, right? So if you FOIL it, you would end up with that. And of course, that is a polynomial, because all the terms are just added and subtracted, and they all have x to different powers. Now you can see that the leading coefficient is a 1, and the highest power is a 3. Hence, this would be a cubic, the degree would be 3, and the leading coefficient is a 1. Now, it's nice that we can have GeoGebra do this. Remember, GeoGebra is really good at this sort of thing. It has expand, it has an expand command, and you just type in the expression that you want to see expanded, and it will do that for you. But what about if we don't have that? How would I get it for this one? Remember that when you're multiplying, when you're foiling something, you basically need to multiply everything by everything else. right? And then you need to do this times that one, times that one, times that one, and times that one, right? So you'd need to multiply every term by every other term in the other brackets, right? So you can shortcut this if you take the highest term here, the highest term here, and the highest term here, and simply multiply them all together. Here we would get 3x to the 4, right? And then we get plus dot 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 dot, a whole bunch of other stuff. But you know what? We don't need any of the other stuff because all we need is the leading coefficient and the degree. So I don't need to fully expand this. I just need to multiply the highest powers of each blob. Here, for example, x makes x cubed, and that's the answer that GeoGebra produced for us, right? It was x cubed with a 1 in front. Here, what we're going to be looking for is, again, we will have a quartic, which is degree 4, and the leading coefficient is a 3. Now, again, you can do what I just did, where you sort of do a little shortcut there. You can also just, we can also just get GeoGebra to do it for us. So x squared, x minus 2, and 3x plus 2. And then you can simply expand that, and of course, it begins with a 3x to the 4. I actually don't care about the rest of it, at least not for this activity, because all I need to know about it is what did it start with. It started with a 3 times x to the power of 4. Alright. Next, it's asking us to explain why these are not polynomial functions. Okay? So again, this term is fine, this term is fine, this term is not fine, and you would say the power of x is negative. And thus not a whole number. Right? We were told that powers of x had to be whole numbers, namely integers including 0 and positive only. But this is a negative number, you can't have that. This one you could reject for two reasons. You could say it's x to the minus 1, because those are actually the same, right? 1 over x and x to the minus 1 are the same thing. So you could say it's x to the minus 1 and then give the same answer I just gave. You could also just leave it the way it is, and you could say there is a variable x in the denominator, and that's good enough. You can't have a variable in the denominator if you have a polynomial. Okay, that's just not. You can't do that. Okay, how about this one? This one is not a. This one is an exponential function. An exponential function. How do I know that? Is because x is in the exponent, not in the base. Like x squared is a polynomial. 2 to the x is an exponential. An exponential function is not a polynomial, so no problem. You just say the variable cannot be in the exponent. That's a different type of function. It doesn't create a polynomial, it creates an exponential. So that's it for these ones. So again, can't have a negative exponent on x, can't have x in the denominator, can't have x inside the exponent. That's a different type of function altogether. So none of these are polynomials, and we sort of look through the three reasons there why not. Now, one of the bigger skills for this section is to figure out if something is figure out the degree of a function using a table. Okay, so let's just put this up here as like a big skill for a second. So the big skill for this section is determine the degree from the table. Okay, so that's going to be the big skill that I'm going to ask here. So I think there's a good example of it in the assignment. Maybe we can take a look at after. This one, okay. So now, in the example we're about to do, we're not you know, like we already know the degree. This is clearly a degree 1, right? In the examples here, what we're doing is we're going to develop why this works, and then we'll show how you can use it in an example. So this, of course, is a linear function. It is degree 1, and it's not that hard to figure out. This would, you just take all the x values and add 1 to them, right? So f of x is x plus 1. You just take the input and add 1. Now the key thing to pick up here is that if you take each term and subtract the term above it, 6 take away 5 is 1, 5 take away 4 is 1, 4 take away 3 is 1, 3 take away 2 is 1. This column here, I'm going to call the first difference, or let's say first differences. Okay, and this is how you create the first differences of a function. You start at the bottom, work your way up, and subtract each term. Subtract the term above it from every term. So 6 take away 5, 5 take away 4, 4 take away 3, and so on. Since the first differences are constant, so they're all the same, right? They all came out to 1. The function must be linear. Okay, and of course we knew it was linear already because they told it to us, but you imagine we didn't know that. So 1, 2, 2, 2, 3, 3, 4, 4, 5, and so on. And what you get there is a straight line, and there's nothing really, incredible about this. We've known this for a long time. That's how you knew how to do slope in grade 9, right? It's just a first building block for what we're about to do. So therefore, the first differences of a linear function are constant. Okay, so that's what we just demonstrated. Now this time, let's try the same approach with a quadratic. So what would be the approach with a quadratic function? So once again, we're doing x squared plus 1, so this would be 5, 2, 1, 2, 5, right? Take the number, square it, add 1. Now let's do the first differences, okay? 5 take away 2, so let's write it out this time. 5 take away 2 is 3. 2 take away 1 is 1. 1 take away 2 is negative 1. 2 take away 5 is negative 3. Now this, remember, is our first differences. You can see that unlike the previous example, they are not all the same. So we go to the second differences. 3 take away 1 is 2. 1 take away negative 1 is 2. Negative 1 take away negative 3 is also 2. And thus we have what are called the second differences. Okay, now here you can see the second differences are constant. They're all 2's. And here we would say the second differences of a quadratic function are constant. Okay, and then what that means is you can identify that this table, even if you didn't know the function, you could tell that this is a quadratic if you went through these steps and determined that the second differences were constant. Now drawing this, I don't know why they want us to draw it, but it's there. It doesn't matter. I wouldn't worry about that. Okay, so the first differences, we tried it, they're not the same. We moved on to the second differences, and of course we find that the second differences are the same for a quadratic. Now, as you might predict, with a cubic, and by the way, to make this work really, we're going to need another box because we need more information. So let's put a 3. You can just add that at the bottom. And this is a cubic. And if you're not familiar with it, a cubic looks something like this. Okay. And we'll look more at cubics in time. When you cube negative 2, you get negative 8. You cube negative 1, you get negative 1. 0 cubed is 0, 1, 8, and 27. Okay. Now, like before, we're going to do a first differences. Start at the bottom, work your way up. 27 take away 8 is 19, 8 take away 1 is 7, 1 take away 0 is 1, 0 take away negative 1 is also 1, negative 1 take away negative 8 is 7. Okay? Obviously those are not constant, so we'll go to the second differences. 19 take away 7 is 12, 7 take away 1 is 6, 1 take away 1 is 0, 1 take away 7 is negative 6. You can see those two are not constant. We'll do it again. 12 take away 6 is 6, 6 take away 0 is 6, 0 take away negative 6 is also 6. And you see that here you get the third differences are all constant. They are all 6. Okay, so here we'll say the third differences of a cubic function are constant. So what this is good for, right, is when you're given a table, you can determine what kind of function you're looking for. And I'm going to add one small piece to this lesson, and then that will be it for this one. So, for example, like down here, they give you some tables, and they don't tell you, what function this is. So it's up to you to recognize what kind of function you're looking at. And to do that, you would do this first differences and second differences and third differences as needed. And of course, if third didn't work, you would go to fourth, right? And if fourth doesn't work, look for a mistake, because I could ask you to go further than fourth, but I don't think it's really necessary once you can see that you can do it with 4. That's usually enough. Let me make, there's one more thing that we can do with this, though, before we leave it for now. And that is that you can also tell, so you can also determine the leading coefficient of a polynomial from the table. So let me just show you how to do this, and then that'll be it for now. So what we're going to do here is let's do another cubic, I think, except let's hide it so we won't see what it is, and we'll say random between 1 and we don't want it to be too big, so let's say between 1 and 3 x cubed plus random between negative 3 and 3 x squared plus random between negative 5 and 5 x, and then plus 2. Whatever. Okay, now let's make some points. So 1 and f of 1, 2 and f of 2, 0 and f of 0, and negative 1 and f of negative 1, negative 2, f of negative 2, and then let's say 3 and f of 3, because we're gonna need a few more points for this to work. So again, we kind of know that this is a cubic already, because that's how I designed it, but we don't know its leading coefficient. Sorry, I thought we drew 3 and f of 3. Okay, so let's take all these values and we'll get them to show. So value. Okay, so here we've got a table, and you can see that. Let's just copy it down as a table first. So let's start with, so here's an example. Negative 2, negative 1. Okay, so just realizing there's a negative 2, negative 1, 0, 1, 2, and then we're going to need a 3. Okay, and then the numbers we got were negative 24, negative 2, 2, 6, 28, and 86. Okay, so this is whatever function. I know the leading coefficient is a 1, a 2, or a 3, but I don't know which one, right? Because we had it draw it randomly. Well, we will check it after. Hopefully it won't just erase it, but it doesn't really matter for what we want to show. Now, of course, the first thing you're going to do is when you look at a table like this, you're going to have to figure out what sort of function you're looking at. Now, I know this is a cubic because that's how I built it, but when you think about it on a test or something like that, you wouldn't know that. So 86 subtract 28 is, what would that be? 858, right? So that would make 36, yeah. Okay, so then 28 take away 6 would be 22. 6 take away 2 would be 4. 2 take away negative 2 would also be 4. And negative 2 take away negative 24 would be positive 22. Okay, that obviously doesn't work. We know it's not linear. So we look at the next one. 58 less 22 is 36. 22 less 4 is 18. 4 take away 4 is 0. 4 take away 22 is negative 18. Again, it doesn't work, so we do it again. 36 take away 18 is 18. 18 take away 0 is 18. 0 take away negative 18 is also 18. So we have three constants. So we have the constant third difference, and that means we're looking at a cubic. Okay, so far so good. We knew that because I created it with a cubic. What's its leading coefficient? The leading coefficient of any polynomial is d over n factorial. Okay, now what does that mean? D is the constant you find from the table, and n is the number of columns you used. So in other words, n is the degree, right? Basically what we just went through is that if you only need one column, you're degree 1, you're linear. If you needed 2 columns, you're degree 2, you're quadratic. If you needed 3 columns, you're cubic, and if you needed 4 columns, you're quartic. So n is going to be 1, 2, 3, or 4 in any of these questions. Like I say, I'm not going to give you one that goes to 5, just too much time to be used. So let's write down what we know here then. So the leading coefficient of my example would be 18 divided by n factorial. Now, what does n factorial mean? Well, n is 3, right? So I'm going to write 3 factorial. What does factorial mean? Factorial means you start with that number and multiply by every single number lower than it, every single integer lower than it, all the way down to 1. So for instance, if I asked you to do 5 factorial, you would do 5 times 4 times 3 times 2 times 1. If you were to do 8 factorial, you would do 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. Okay, that's 8 factorial. Here, we're just looking for 3 factorial. So 18 on the top divided by 3 times 2 times 1, which is 18 over 6, which is 3. So we know the leading coefficient of this cubic equals 3. So this cubic, we don't know the whole cubic yet, by the way, but we know that it must start with 3x cubed plus dot 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 plus dot 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 plus dot dot dot, right? We don't know what comes after it doing this method yet, and this is kind of enough. Like, let's stop once we know the leading coefficient and the exponent, but that would be how you would do it. Okay, so let's confirm that we're right. And you can see that the cubic that the computer created for us does indeed start with a 3, right? And it starts with a 3, which we were able to figure out without knowing that by using this technique here. The leading coefficient would be whatever your common difference is, so 18 in our example, divided by the factorial of the degree. So let's just make a quick chart over here. 1 factorial is 1, 2 factorial is 2, 3 factorial is 6, 4 factorial is 24, and 5 factorial is 120. I can't think of a reason why you would need to go. You don't even think you need 5, honestly, but that's 1, 2, 3, and 4, just in case you need them. And you can see, if we go back up here, if you take d value divided by 3 factorial, you get 6 over 6, which is 1, and that is in fact the leading coefficient of this one, right? It starts with a 1. This one starts with a 1, and if you look at its d value, which is a 2, its n value is also a 2, you get 2 over 2 factorial, which is 2 over 2, which is 1, and that's your leading coefficient, right? So this will work always. It's a good way to find the leading coefficient of a polynomial based on the table, which is something you may need to do in your assignment or on your tests. Okay, so I know it's something we're adding to the notes, but it's a skill I think you can master. Okay, so there's some practice here. Otherwise, there's some homework that's right here. Just the 2 questions for homework, and then the practice handout, and then the assignment for that section. We can just take a quick look at that here. So the unit 2. So there's a leading coefficients here, right? So we could try this one. So here's a table of values. What's the value of the leading coefficient? 2, 4, 5, or 3, right? Based on that table. So you just do the same technique we just did. Okay, family of polynomials. We haven't got to that yet. We haven't done this yet. We haven't done that yet. So really, this is the only question you could do at the moment. So I wouldn't worry too much about it right now. Just make sure that when you do open this up, you go back to this lesson 1 and look at what it's asking for would be the technique we're using here.